Okay, any questions? Let's start.
Yeah.
No?
So for tomorrow, for the morning class, their lab ends at 1, right?
Yeah.
And then our class starts at 2.
Right.
Can we do stuff in between that? Or?
No, I have a meeting at that time, 1 to 2. Unfortunately, no. Well, maybe. It depends if there's more than one person. Stop by, you could check. Why, you have a class until then? Or something?
Oh, no, I'll be there. I'll be there before, for sure.
Okay.
Do we get the whole period to do that, or is it just...
No, not the whole period. I have to talk about some of the reactions. Okay, other questions?
When we finish the lab, do you want us to come and tell you like what's in our unknown solution?
No, you'll do that later.
Oh, okay.
Okay, you can look at your results and then I'll talk about the report.
Cool.
Morning lab period depends on how long I talk. Officially it starts at 9:30 and then goes on. But if, I might talk for half an hour to an hour at the beginning. 10 to 10:30. Other questions? Depends on how far people are along. If most people are almost done, then I'll talk for an hour. Where did we leave off last time? The 100 milliliters of water? Was that it?
Oh, you were beginning to tell us how H2PO4 minus, the pK is 7.20 and then the pKb is 11.85.
Oh, okay.
Yeah.
H2PO4 minus. So we end up having a buffer that consists of HPO4 2 minus and H2PO4 minus, right?
Yeah.
Yeah.
Both of these species are amphoteric. And so what the point of what I was trying to make earlier is this. Even though both of these are amphoteric, they're only going to behave one way in this mixture. And that is, this one will behave as the acid, and this one will behave as the base, even though they both can behave both as an acid and a base. And the reason they behave like this is because of this. Yeah, it has to do with charge too, but the reason they behave this way is this. If you're a base, and we have two acids here, if you're a base and we have two acids, which acid is going to be easier to attack? The stronger one. And so if you're a base, then you're always going to attack this acid, never this acid, because this acid is stronger. So even though this is amphoteric, we only consider it as being an acid because of the mixture, what it's mixed with. Likewise, if you're a acid, which one of these two bases will have an easier time plucking a proton off? HPO4 2 minus. And so this one will always act as a base. And so the role depends on what the mixture consists of. You know, yes, it is an acid and a base, but in this case, this one only reacts as the acid, this one only reacts as the base because of the mixture constraint. So, yeah, they have a pKa and pKb, but we don't even pay attention to that. We just look, you know, what's the strongest acid present, what's the strongest base present. All right, the next thing we're going to look at is, do buffers work? And to see this, let's take a look at an unbuffered solution. Like 100 milliliters of water to a liquid. And then we'll add 1 drop of 6.00 molar HCl to this. Will the pH change much or a lot? What do you think? For the water. If I add a drop of HCl to it, will the pH change? Yes. Will it change significantly? Well, let's see. We're going to do the calculation. And so in chapter 17, we have to do a new step all the time. We'll call it step A. Step A is solution dilution. And so here, for solution dilution, we always calculate the final volume. The final volume of this is going to be 100.05 milliliters, because a drop of water is about 0.05 milliliters. And then we calculate the new concentrations. So HCl. HCl is going to be significantly diluted because we start off with a volume of 0.05 and then we dilute it to 100.05. And so it has something called a huge dilution factor. The dilution factor is original, 0.05, over the new 100.05 times the original concentration, which is 0.100 molar. And so this dilution factor is huge, 5 parts to 100,000 parts dilution. And that's going to change the concentrations significantly. Oops, this wasn't 0.100. What was the original? 6.0 molar. 6.00 molar. That's going to give me what? Yeah, so the HCl is diluted significantly, and now let's go ahead and figure out what happens here. HCl is a strong acid, and so we'll just have a Ka for this. HCl plus H2O liquid goes to H3O plus Cl minus. What is Ka? Very large. And so our initial, this is initial after dilution. And so our initial starting concentration would be for whatever reaction we're looking at, in this case HCl and water, it's 2.99 times 10 to the minus 3. H2O is liquid, this is going to be 0 molar, 0 molar. Since K is very large, it's complete, so we lose all of the HCl, and we form 2.99 times 10 to the minus 3 molar hydronium, and 2.99 times 10 to the minus 3 molar chloride. I'm only allowed 1 sig fig, but I don't want to round to 1 sig fig. Rounding to 1 sig fig introduces significant round-off errors. And so we never round to 1 sig fig, we'll just carry some extra digits. Are you going to worry about water, KW? Do you think water would contribute much hydronium to this? No. I mean, this is 10 to the minus 3. Most water that can contribute is like 10 to the minus 8, 10 to the minus 9, something like that. And so water is not going to really contribute much. So we're just going to stop here, calculate the pH, assuming that the amount of hydronium we get from water is negligible. The pH comes out to the negative log of this, 2.99 minus 3, which gives us pH 2.52. So, did the pH drop significantly? Yes, because originally the pH of pure water should be 7.00. kW is the only source of hydronium in pure water. But with the addition of 1 drop of 6 molar, the pH dropped from 7 to 2.5, which is like 4.5 orders of magnitude, which is like 10,000 times to 100,000 times more acidic. And so now our water is 10,000 to 100,000 times more acidic. And so we call this, there was a significant pH change here. And this is an unbuffered solution. Now, what a buffer does is it minimizes, or tries to minimize the pH change. And so let's repeat the same problem, except to our buffer that we just did the calculations for. And so now I'm going to add 1 drop of 6.00 molar HCl to a beaker that contains 100 milliliters of buffer, pH 7.00. And the buffer is going to contain the base component, HPO4 2 minus, at, what was it, 0.517 molar. And the acid component, H2PO4 minus, at 1.00 molar. Were those the numbers we got? This made the pH 7 buffer? It just has to be this ratio. You know, I could change the concentrations to whatever I want. It should be this ratio. So I do the same thing here. Step A is solution dilution. So let's calculate the new concentrations. So I'm going to end up with 100.05 milliliters before. And the HCl should be the same. It's a 0.05 to 100.05 dilution of 6.00 molar, which gives us 2.99 times 10 to the minus 3 molar. Okay, but now we have other components in this mixture. We have HPO4, HPO4 2 minus, which is going to equal this. What is the dilution? So HPO4 minus started off at 100 milliliters and was diluted to 100.05. Was that a very significant dilution there? 100 to 100.05 was a negligible dilution. And so what some people do is they say, well, it's such a negligible dilution, the concentration really didn't change much. But, you know, for accuracy, we're going to go ahead and calculate that. Even though it is a very small change, we're not going to ignore it. And so this is going to be 0.517 molar, which gives us a new concentration of 0.516? 67? Okay, thanks. Same thing with H2PO4 minus. It's a very small dilution, 100 to 100.05 dilution of 1.00 molar, which gives us 0.9995 molar. They're very small dilutions there, but a big dilution for the HCl. Okay, after step A, then in chapter 17 we do step 1. Step 1 is always kind of the same thing. Step 1, we react the strongest acid with the strongest base present. And so let's go ahead and do this. What is the strongest acid present? Well, there's a water present also. So we've got to consider water because that can be an acid or a base. So the strongest acid present would be HCl. And the strongest base present is it's not water. We could consult the chart up here too. Or, you know that the buffer is a base to acid ratio. What was the base that we called the buffer? HPO4 2 minus. So the strongest base presence is HPO4 2 minus. And so what does this form?
Hydronium and PO4 3 minus.
Not hydronium. This is different. This is not a Ka equation. Yeah, it's going to form, well, protons going to be donated to form H2PO4 minus plus Cl minus. Is this a Ka? Or is it a Kb? It's neither. Ka is acid plus water. Kb is base plus water. In the previous chapter, the strongest acid or base present that the added acid or base reacts with was water, because there was nothing else present. So it was always water plus the acid or water plus the base. In this chapter, we're going to have stronger species than water. Water might not be the strongest base present here, and it wasn't, because this is a stronger base. In fact, this is even a stronger base. And so this is not a Ka, it's not a Kb, this is just K for reaction. Okay, what is the K value for this reaction? Large? I want a little more specific answer, qualitative answer. Very large? This should be automatic. Didn't you see this? I mean, this was covered a couple of weeks ago, I think.
Is it neutralized because it's a strong base with a strong acid?
No, it's not a strong base with a strong acid. It's a strong acid with a weak base, and you should know the K value like this, right? Because you should have seen it more than once, I would think. I would think you would see it more than once if you reviewed your notes. If you haven't reviewed your notes, then maybe you haven't seen it.
Is it like 1.8 times 10?
No, that's a good one. That's the acetic acids. Ka value. This should be automatic. It should be, but
Very, very
very, very large, right? Very, very large. Yeah, it's very, very large. Right? Not just large, but very, very large.
Do we only use the very, very large, or the triple V large, to distinguish between like strong acids, strong bases, strong acids, weak base, water and strong acids?
No, we use that when we start to look. When we get a very complicated mixture, then we got to compare a very, very, very large versus a very, very large. The very, very, very large is going to be the first reaction. We do it to rank the reactions that we get in mixtures. And so this is why I did that, the very, very, so that you can have some kind of perspective, that you could at least rank these qualitatively. Maybe not put numbers on there, but at least do it qualitatively. And try to visualize what's happening here, in terms of driving force. The reason we want to start doing this is because later on we are going to be putting numbers on the driving force. And so if you have a good qualitative idea of what the driving force should be, then you can see, does your answer make reasonable sense? Well, anyway, going to HCl, we have 2.9. Actually, let me rewrite this as 0.00299. 299 molar. HPO4 2 minus is 0.5167. H2PO4 minus is 0.9995. Chloride is 0. So the change here is going to be complete. What's the limiting reagent? HCl is the limiting reagent. So this drops to 0 molar. We consume the limiting reagent. And these are all 1 mole ratios. So this is going to be minus 0.00299 molar, which gives us what? 1, 6, 7, 3, 0.51371
Yes.
molar for this. And then over here we add this 00299. We're going to get 9410249. Double check that one.
Isn't it 00249?
100249. Okay. 100249. Okay, thanks. And 00299 molar. All right, this is step 1. Now we got to think about step 2. Step 2, we usually just repeat, repeat or etc. If we repeat, let's take the strongest acid present and react it with the strongest base present. And so what is the strongest acid? We don't have any more HCl. So HCl is no longer the strongest acid. It's been completely consumed. H2PO4 minus. And so we'll take H2PO4 minus and react it with the strongest base present, which is HPO4 minus. And we get, what do we get from this? We're going to get HPO4 2 minus and H2PO4 minus, which is the same thing, so nothing's going to happen here, right? NR. So are we done?
About what? Then we go to the next one.
Well, now what do? Do we do Ka for H2PO4 minus and then Kb? Or what do we do? Or we recognize something. We recognize that what we're left over with is a weak acid and a weak base that are conjugates of each other. And so, or this is what we call a HH buffer. That's a Henderson-Hasselbalch buffer. And so I don't have to do an ice table for this. I'll just go ahead and use the Henderson-Hasselbalch equation. And so that is the pH is equal to the pKa, which was 7.20, plus the log of the base. The base is 0.51371 over the acid, which is 0.100249.
It's 1.
I'm sorry?
1.00.
Oh, 1.0. Yeah, you're right. 1.00. 1.00249. What did you get?
6.90.
6.90. So the buffer, originally the buffer was at 7.00, now it's at 6.9 with 1 drop of 6 molar HCl. Whereas the unbuffered solution, we saw significant changes in pH. In a buffered solution, we see small changes. And so the buffer, what it does is it buffers the action of added acids and added bases on the pH. And so it tries to minimize the pH changes.
I didn't exactly catch why we use 7.20.
Oh, that's the pKa.
Oh, okay.
That I just wrote it. I skipped a couple of steps. pKa. I should have written out the equation. pH is equal to the pKa of the acid component plus the log of the base to acid ratio. So the acid is H2PO4 minus, the base is HPO4 2 minus. So this is what we have. Now, what ends up happening is this. When I add an acid, strong acid, when I add a strong acid, then the pH is equal to the pKa plus the log. Now the acid will take out some of the base. And so I'm going to have initial base concentration minus X, which is the amount of acid I add. And that's going to increase the acid concentration plus X here. And so I lose some base here, I gain some acid here. And so I have a minus X here and a plus X here. Now, let's talk about capacity. I could have had the pH start at 7 and end pretty much at 7 if I did this. The pH depends on this ratio of base to acid, right? And so all I need to do is, if I made this like a billion molar, if I made this a billion molar and I lose a little bit, and this is a billion molar here, losing a drop or gaining a drop, if you have a billion drops, is that going to make any change in the ratio? No. And so the larger the capacity, the more the ratio is resistant to changing, the more stable the pH is. And so if I could keep the same capacity. Let's say I had a thousand drops, and I remove a tenth of a drop. It's not really going to do much. And so the higher the capacity, that is, the more concentrated it is, the more resistant to changes the pH will have. And so I could have made this an even higher capacity buffer. Rather than starting off with half a molar and 1 molar, I could start off with like 5 molar and 10 molar. If I did 5 molar and 10 molar, then losing this much and gaining this much won't have much of an impact on the ratio. Whereas the opposite, if I made the buffer more dilute, then I'm going to see more significant impact on the ratio. And so let's say I made this 0.005. If I made this 0.005 and I'm losing 0.003, then I just lost 60%. And over here I'm going to be gaining 30%. And so that's going to result in a big change in this ratio, which means a more significant deviation from pH 7.
Sometimes they wouldn't work, right?
What's that?
They wouldn't work sometimes?
Yeah, it wouldn't work sometimes, exactly. And so the buffer capacity is important. To make things more concentrated costs more money. Sometimes it's not practical. For example, can you make a 100 molar solution? Can you make a 1,000,000 molar solution? Sometimes it's impossible. All right, so making it the buffer higher in capacity costs money. And so if you were to buy a pH 7 buffer, you don't know what you're getting. You know, if you get a pH 7 buffer, what's the capacity of that buffer? Has it been watered down so much that it has very little capacity? Or is it fairly concentrated? It's like if you buy a liter of helium. If you buy a liter of helium, you have no idea how much helium you're getting. Because in that liter of helium, did they just put 1 atmosphere, half an atmosphere, a tenth of an atmosphere, or 1,000 atmospheres of helium? You know, and so it's still a liter of helium, and this is still a pH 7 buffer, but the capacity can change quite a lot depending on what you get. And so you could water this down and still have a pH 7 buffer. Quite a lot. Sometimes you can overwhelm the capacity of the buffer, and so let's take a look. There's another problem here. It's with HCl. Okay, let's try this one. In the next example, we're going to have 100 milliliters of the pH 7 buffer with the capacity. The capacity is just the concentrations for this, and so it's going to have the HPO4 2 minus the same 0.517 molar, and then the H2PO4 minus at 1.00 molar. But this time we're not going to add 1 drop. This time let's add, sorry, how much should we add this? I'm going to go with more than 4 drops.
400.
400 might be too much.
10.
Let's go with, yeah, milliliter.
19.
19.
19. 25.
19 drops?
Yeah.
Let's go with more than that. Let's go with,
30.
I'm going to go with 15, let's go with 15 milliliters.
Okay.
And in this case, let's go with sodium hydroxide. 6 molar sodium hydroxide. It works the same as with the HCl, except now you just attack something different. And so why don't you go ahead and try to work this one out. I'll give you a few minutes to do that.
Okay.